All right, in this video, we're going to start setting up a framework for how we're going to look at applications of the definite integral. We're going to start with just a reminder about how Riemann sums work. We're going to go back to Calc 1, set up these Riemann sums, remind us of the definition of the definite integral, and then we'll start to use that process to set up an integral formula for the area of the region bounded by two curves. This is not something that would be difficult in general. My guess is that if I just started with this problem of an area between two curves and had you all think about it for a while, you could come up with a pretty easy integral formula for it. So the goal here is not just to build the integral formula, it's to build a process for finding these integral formulas using a small example that in that way, we'll hopefully be able to replicate this for more difficult examples. And then we'll look at a little change of variables and integrating with respect to y at the end, and we'll talk about when that might be useful. So first, a reminder about Riemann sums. Let's say that we're interested in finding the area bounded between the graph of f of x, this one here that I've got pictured, and the x-axis between x equals 1 and x equals 4. So we'll just say, like, we're looking right here. I missed that one a little bit. Let me grab it from the bottom up. That'll be a little easier. So we're trying to figure out this area. Oops. I always forget to turn off my straight edge shape. We're looking for a way of finding this area. This is not too bad. We know how to do this with definite integrals, but what we're going to do is remember, how did we start this when we were talking about Riemann sums in Calc 1? And what we did was we split this up into a bunch of rectangles. Let's say we want to split this up into, I don't know, let's call it 6 rectangles. We'll look at a rectangle right here. Maybe I'll use my straight edge shape again. There's one rectangle. Here's 2 rectangles. 3 rectangles. 4 rectangles, and here's my 5th one, and then lastly I've got my 6th one right here. I should draw this edge down. Alright, and if we looked at the area of these 6 rectangles, added them all up, we'd be able to get an approximation of our actual area. And so we might need a width of each rectangle. We'll call that delta x. That's going to be b minus a over n. So for us, delta x is 4 minus 1 over 6. 3 over 6 is a half. And we can see that, right? Delta x is just this little width of each of our rectangles. We would also need heights, x sub k star. These x sub k stars are going to be the values that we choose on our partition. So let me draw up a little regular partition between 1 and 4. We'll split this up a bit. So here's 2 and 3, and then we have all of our half marks in between. And so here's how we divide this up into 6 rectangles, and it looks like for us we picked a right Riemann sum, and so we picked the rightmost x values on each of these subintervals. But you might remember that we don't need to do that. We don't need to pick the leftmost values or the rightmost values or the midpoint values. We can literally just pick any x value. So we could have done like this one, and this one, and this one right in the middle, and maybe on this one we pick 3, and on this one we pick something a little bit bigger than 3, and then maybe on our last one we pick 4. Who cares? And we could get all these x values, plug them into our function to get the y values, and then our Riemann sum becomes a summation from k equals 1 up to n of f of x sub k star times delta x. This is just a sum of all of the heights times the widths. This is a sum of all the areas. And so the way that we normally would build up to that is we'd say the area of the kth rectangle is going to be f of x sub k star delta x. So if you make k equal 1 or 4 or whatever, you're going to get the area of that singular rectangle. Our total area is approximately this Riemann sum. And when we wanted to find the actual area, what we did was we looked at a limit as n goes to infinity of this Riemann sum. And you probably did this in Calc 1, maybe at least one time. I know I always make my Calc 1 students go through a problem like this where they see the limit, but this ends up just being the definition of the definite integral. And so we stop using this limit definition of the integral pretty quickly because it gets really difficult to use, and we come up with other ways of showing this. Then the fundamental theorem of calculus kicks in, and we tell us, how do we evaluate these? Well, we know antiderivatives and endpoints, plug them in, blah, blah, blah. But setting up this integral took a little bit of work, making sure that our Riemann sum actually does have a limiting value of the actual area that we care about. Okay. So I think that was all I wanted to talk about. So we have this slice and sum strategy here. That's what I like calling it, and you'll see that repeated in other places as well. That is not my own term. I just think it's a cool one and a good one. What we're doing is we're slicing that area up into a bunch of different pieces, finding the area on each piece, and adding them all back together. This is really one of the biggest main ideas of calculus, that we can do this kind of thing. For continuous functions, we're allowed to do this. For lots of different things, we can cut it up into a bunch of pieces, find the value of whatever we care about on each piece, and add those all up. So for us, when we wanted to find the area of a region under a curve, we cut that region up into a bunch of rectangles, find the area of each rectangle, add them all up, and then we looked for the limiting value. So we're thinking of infinitely many, infinitely thin rectangles here. We're going to apply that same sort of slice and sum strategy to find the area between two curves. So what we'll do is we'll look at two functions. We'll call this black one f of x and the green one g of x. And we've got that f of x is always greater than g of x. Now in this picture they're not, but they will be on an interval that we pick. So I'm going to say a starts at here and b goes to here. So we don't really care about the fact that they cross over each other outside of the interval, because on this interval, both of these functions are continuous, and f is greater than g. We want to use the slice and sum strategy here to find an area between these curves. So we'd like to evaluate just this area. We're going to use a Riemann sum again, and the way that we're going to do it is we're going to draw a whole bunch of rectangles again. I'll only draw a couple, because that's all we really will need. What you'll notice is that if we drew a whole bunch of rectangles that spanned from the leftmost edge of this interval to the rightmost edge of this interval, we could add up the areas of all of these rectangles. Now, to do this, we need to find the area of the general kth rectangle. We're going to make a couple of assumptions. The first is that our delta x is again going to be b minus a over n, meaning all the widths of our rectangles are going to be the same again. It makes it way easier for us. Now, our area of our rectangle is going to be the height of each rectangle times the width of each rectangle. So we have to figure out a way of finding the height. Well, on each of these rectangles, we have these x values. I tried to draw them in line with where they are on each. So it's the same x value on the top and the bottom here. We'll call this our x sub k star. And you'll notice that the height is just a difference in y values. So it's going to be f of x sub k star minus g of x sub k star times delta x. Again, this x sub k star is fulfilling the same purpose that it did earlier. This is the x value that we're picking to represent this specific subinterval that we had in our partition. So remember, on this slide here, all those red dots, we picked the rightmost x value. On the blue ones, we just picked a random x value from each one, and that's fine. We have the same thing going on here. Pick an x value in each subinterval, plug it into both f and g, and we'll pretend that that's representing the height difference of those two functions on that interval. Then we'll say once we have that, our total area is approximated by the sum of these things. So if we add up all of these areas, what this really is just a sum of all the a sub k's for k equals 1 up to n. Add up the areas of all those rectangles. That's going to approximate that area that we cared about. And how do we get the exact area? Easy. Apply a limit. If we make n go to infinity, then by the power of Riemann sums and the definition of the definite integral, this is going to turn into a definite integral from a to b, our starting and ending point. That part's baked into our delta x, of f of x minus g of x dx. Notice that our delta x turns into a differential, dx. You might remember that from Calc 1, the definition of a differential. It's this infinitely thin delta x, essentially. And they'll also notice that we lose the x sub k stars, and that's because now we're not looking at some subinterval of x values that we have to pick one from. All of those intervals collapsed onto each other, and so we look at each x value specifically between a and b. So we change the notation a little bit, right? Our summation turns into an integral sign. We have to include the limits of integration on here, and then we have our dx instead of a delta x, and we lose those x sub k stars because we're not picking a value to approximate the heights of these functions on the subintervals. We can look at the actual exact height at each value. All right, so all this to say, if you want to find the area of a region between curves like this, between a and b, we just have to integrate the difference of functions. That's something that you probably could have figured out pretty quickly, though, by just looking at this kind of a picture, right? If you look at the integral under the black function, it's both of those areas shaded in, and if we just want the red area, then just subtract the integral under the g function. So sometimes you'll see people do it this way. They'll split this integral up, which is fine. I always think it's easier to combine this into one integral. Most of the time, the functions that we're looking at will be able to be combined nicely. Anyways, let me read this off. So if f and g are continuous functions, and again, f of x is greater than or equal to g of x on the interval a to b, then the area of the region bounded by those two graphs is the integral of the top function minus the bottom function. Cool. So this is a model for how we'll set up these integral formulas. We're going to slice this up into pieces. We'll look at the the accumulation on one piece. In this case, it's the area. Then we'll use that to approximate the total area, and then we use a limit to get an actual integral formula. Here's a couple of examples that we can look at just to make sure we know how this is going to work. So let's say we want to find the area of the region bounded by these two graphs. What I'm going to do first is just sketch them, partly so we can see what our limits of integration are going to be, and partly so that we can see what the functions are in terms of their ordering, which one is greater than the other, but also just because it's good to get a good picture of what we're looking at. I always think it's nice. So our 5 minus x squared is going to be 1, 2, 3, 4, 5 up here. Oops, I don't want this straight line thing on. It's going to be this nice upside down parabola. And x squared minus 3 is going to be an upwards facing parabola here. So what we're looking for is this area in between. Hopefully, it's easy enough to see that this function is the top one and this one is the bottom one. So when we set up our integral, we're going to be setting things up with the integral of 5 minus x squared minus x squared minus 3. And then what we need to do is figure out what these values are, specifically what the x values are here. You can do this in a lot of cases by just like some guess and check, right? You can kind of take a peek at it and just see what it looks like. Or what you can do is actually just set the functions equal to each other, because we're looking for intersection points, right? You guys have done this in algebra classes from days gone by. And what we end up here is 8 equals 2x squared, or x squared equals 4, which gives us x equals plus or minus 2. So we'll go from negative 2 up to 2. Here we go. Not too hard to set this thing up, right? I'm going to simplify this a little bit by just subtracting all my like terms. 5 minus negative 3 is really 8. Negative x squared minus x squared is really minus 2x squared dx. Now I can anti-differentiate this thing. I've got 8x minus 2x cubed over 3, and I'm going to evaluate this from negative 2 to 2. You can use a whole bunch of symmetry tricks on here if you'd like. You could just evaluate it from 0 to 2 and double the size of that. That's fine. I'm going to go ahead and just do it the way that it's written. We've got 16 minus 2 times 8, that's 16 over 3, minus negative 16 plus 16 over 3. So we've got 16 minus negative 16, that's going to be 32. And then we have minus 16 thirds minus 16 thirds. That's going to be minus 32 thirds. All right, so what is this? 16 plus 16 was 32 minus 32 thirds. So that's going to be, is that 64 thirds? Is that right? I think so. It's 32 times 1 minus a third, 32 times 2 thirds, 64 thirds. That's the size of this blue region that we've got here. All right, here's an example. This one's a little bit trickier. What I want you to do is to pause the video, sketch these two graphs, see if you can find the little trick in here, and then just start this problem. And when you get stuck or when you finish, just unpause the video. We'll keep playing this thing and we'll work on it together. All right, so here's what our picture should look like. You'll notice that when we graph these functions, we end up with two regions because our functions cross through each other. When I was a calculus student, I always heard these described as bow tie problems or bow tie regions because they kind of look like bow ties, right? They have a chunk on each piece and then they come to a point in the middle. And so what you'll remember, hopefully, is that in our setup, in our little theorem that defined how these worked, we needed one function to be greater than or equal to the other on the whole interval. And in this case, they are not, right? Our green function is above from negative 1 to 0, but then from 0 to 1, our red function is above. So what we need to do is split this into two regions. So the first region will go from negative 1 to 0 of our top function x cubed plus 1 minus x plus 1. This is the region with green on top. And then we'll also look at this region from 0 to 1 where x plus 1 is the top function now and x cubed plus 1 is the bottom function. So once we've got this, we can go, all right, let's combine all our like terms. If there are any, we've got x cubed minus x, and then 1 minus 1 is 0. And then for this one, we have the exact same thing, but different signs. So we'll say x minus x cubed. And then you can evaluate both of these things. X to the 4 over 4 minus x squared over 2, evaluated from negative 1 to 0, plus x squared over 2 minus x to the 4 over 4, evaluated from 0 to 1. Notice that both of these, when you evaluate them at 0, it's just 0. So we really only need to say this is 0 minus a fourth minus a half plus a half minus a fourth. So what do we get here? A negative fourth and a positive half. So we have half plus half minus a fourth minus a fourth. So we just get a half out of this, right? Check my arithmetic. I make a lot of mistakes. But there's our region. So you could also use some symmetry on this. You could just look at the size of one region and then you could double it, right? Because we know that this nice cubic function shifted up and this linear function shifted up are going to have this nice almost rotational symmetry around the origin, but now it's a rotational symmetry around that point 1 unit above the origin. No big deal. The areas are going to be the same, right? So that's something that we could do too. Kind of a clever little thing. All right, here's a harder example. we want to find the area of the region bounded by these two graphs and the x-axis. Let me shade in the area so that you can see why this is a problem. We're going to start up here. We're going to look at the area between these two things. But once we get here, we're going to be bounded below by the x-axis now. This is almost like that bow tie problem, because at this point right here, we switch what our bottom function is, right? On this region, our bottom function is the axis, y equals 0. But on the rightmost region, our bottom function is this cubic function. Let me just write in the functions here. This is x plus 6, and this one is x cubed. But then again, remember, we have the x-axis at y equals 0. So we could set this thing up. We'll say, all right, our area is going to be the integral from this point over here up to this point here. So we'll say from negative 6 to 0 of just x plus 6 minus our bottom function is the x-axis, so we'll say 0. And then we have the rest of this area, which is from this point at the origin up to this point right here. This is at 2, 8. So our rest of our area is the integral from 0 to 2 of x plus 6 minus x cubed dx. Let me write that out once nicely. There we go. That looks a little cleaner. And I'll let you figure that part out, because we really just need to anti-differentiate and evaluate from here, and that part won't be too bad. But setting this up is tricky. What a lot of people will do is they'll look at the integral from negative 6 all the way up to 2, but what that would include is our cubic function all the way down here, and we'd have all of this extra area, which we don't actually want. So just be careful about how we set that up. All right, let's do this again. Wait a second, we already did this problem. What you'll notice is that there's some easier ways to do this. What you could notice is that, like, hey, that's a triangle. I don't have to work that hard to find the area of a triangle, right? Half base times height. I can find my height. It's right here. Whatever the y-intercept of this is, that's 6. I can know my base. It's from negative 6 up to 0, so my base is 6. So the area of this thing, maybe I'll say the area of the triangle, is half of 6 times 6. Half of 36 is 18. And then we could just add the area that we have here. Another way of doing this that people will do every now and then, this works out really well when you end up with linear functions, is they'll look at this triangle here. And then they'll just subtract this area under our cubic function. So there's a couple of ways of doing this that you could play with, and they all work out really nicely. But if you're able to, feel free to use some geometry stuff. That really only works when we have nice linear functions, or at least linear pieces of functions, because then we can cut things into some straight edge shapes, and those are the kinds of shapes that we have area formulas for. So the other way that I want to talk about doing this is to integrate with respect to y instead. So, oops, there we go. Let's take a look at this. What we did earlier was we drew a bunch of rectangles that looked like that, right? We're going to flip that around, and we're going to say, what if we drew rectangles like this? And I know my rectangles are kind of bad, but oh well. You can see what's going on. Now, we don't have a delta x, a tiny width. We have a delta y, a tiny height. And we want to find the width of our rectangles. If we are able to invert our functions, this is just a difference in x values, which we could make function outputs by writing our functions in terms of y. So take a look at this. Suppose we've got two functions that are continuous with f of y. Notice that's an x value, greater than or equal to g of y, so that means this black one is f of y. It's not a top function anymore, it's a rightmost function, right? So instead of top, we have right, left, because we're really thinking about big output variables. And if our output variable is x, then the bigger output variable is on the right. Just like if the output variable was y, the bigger output variable is on top. And let's say we've got this from C to D, which are not going to be these points anymore. They're going to be a point here up to here. They're y values. So from y equals 0 up to y equals 8, I believe it was, right? Yeah. So we can set up our integral that way. Kind of cool. Let's do it. So like I said, this is y equals 0, y equals 8. These are functions written in terms of x. We want to write them in terms of y. So I'm going to say x equals the cube root of y. And here, x equals y minus 6. All right, so let me write these out. This one is our cube root. Oops. See, I already messed it up. There we go. And this one, this linear one, is our y minus 6. So now when we set up our integral formula, our integral is going to be from 0 up to 8, because these are y values now, of our cube root function minus y minus 6 dy. And the advantage here is that we can do this in one integral, because when we stack our rectangles this way, we always have the same function on the right and we have the same function on the left. As opposed to when we use skinny vertical rectangles, right? We had this change in our bottom function because we were stuck in above the x-axis. So at this point, remember, we switched to having our rectangles stacked on top of the x-axis instead of stacked on top of this cubic function. But now, if you orient your rectangles in the opposite direction, that part doesn't matter anymore. Again, I can let you check this area. It's y to the 1/3 minus y plus 6 dy. Integrate that, evaluate, and double check it with the area that you found earlier for this same example, and they should be the same. So it's kind of like your own choice here. You get to pick what you want to do. But in a lot of cases, we'll find that changing variables and switching our orientation is actually really helpful. Here, it saves us from having to set up two separate integrals or have to be clever about using some geometry stuff. I don't know if the trade-off is really worth it for everyone in this case, but I want us to see this because eventually that trade-off is going to be really important, where maybe it won't even be possible to set up an integral to measure the thing that we're trying to measure with x as our input variable. Maybe we'll almost have to do it with y as the input variable. So we'll see that later once we hit other topics, but this one, I don't think it's that big of a topic, but it's a nice way of reminding ourselves how Riemann sums work and setting up this slice and sum strategy so that we can put things together to find things like areas. In the next couple videos, we're going to start thinking about other measurements, things like volumes and surface areas and arc lengths. And so we're going to have to think cleverly about how to slice up our three-dimensional objects into some pieces where we can measure the volume on each piece and then add them all back together with a Riemann sum to get some sort of an integral formula. So that's where we're heading. This is just a nice kind of way of setting up a template almost for how we'll find those integral formulas.